Well, so Tiris actually asked me to try to make it a little bit introductory, so simple. So I will start with introducing some concepts and then try to develop some theory regarding the integrability of difference equations. So just to give you the outline of my talk, if it works, right? Yeah, it works, good. So I will start with some introduction. So actually, I'm just going to show you some equations of which arise in various in two different areas of mathematics, and which we can see them as difference equations, and also say a few things about the notation that I'm going to use. And based on these examples, I will describe a class of difference equations that I'm going to consider in this discussion today. And then I will move on to define the integrability of these equations. The notion of integrability is very, yeah, it's not very, I mean, there is not a unique, if you like, definition of integrability. So there are many different criteria and tests for integrability. So, but the one that I'm going to use and discuss today is based on symmetries and recursion operators. And in order to discuss this, I will introduce these concepts, and then in order to derive a so-called integrability conditions, right? I'm just going to introduce a few things about formal series and how the machinery of symmetries and recursion operators will, and along with the formal series, will give rise to what we call here integrability conditions. But the interesting thing is about these integrability conditions is that they don't, it can be used to prove that, to show that a given equation is integrable, but also they can be used as determining equation for the symmetries of the equation. So they have a dual role, and this is really useful in applications. Because from these integrability conditions, I then can derive the symmetries, which then can be used to find particular solutions, which usually are related to discrete Painlevé equations. And this is what I'm going to say a few things about reduction to discrete Painlevé equations. And on the other hand, integrability conditions can be used to classify integrable equations, to find within a certain class of difference equations, the equations which are integrable in the sense of possessing symmetries of higher order. And I just going to show you a small classification problem, which actually lead to an equation to give rise to 4 equations. And then just going to discuss, but before concluding, some extension of this theory to some difference equations and systems of difference equations. And this talk is based mostly on these 2 papers, and this classification problem that I'm going to discuss actually is based on that work that I've done with Sasha Mikhailov back in 2013, which that time we were discussing second-order integrability conditions. Okay, so this is the plan for it. Also, let me start with some notation first of all. Right, I'm going to discuss difference equations. So now my independent variables will be integers, so they will take integer values, and so I will be denoted with n and m, right? And because I'm going to discuss mostly equations which involve 2 independent variables, I'm going to use these 2 letters. And the dependence of a function u on the independent variables n and m will be denoted with indices, like a sequence. Right, at some point I'm going to use when I will discuss Painlevé equations, I'm going to use functions with 1 index, which simply denotes that this function u depends only on a variable n. And if it depends on 2 variables like this one and m, then the index will be, of u will be n comma m, so denoting the 2 values, the 2 independent values on which this function depends. Okay, this is the notation I'm going to use, and the first origin of difference equations for me is a very nice example coming from the wave equations, which I hope that everyone is familiar with. Right, so we have the wave equation, the initial value problem for the wave equation on the infinite string, right? And the solution for this the initial value problem is given by the D'Alembert formula, by this nice formula here. Right, we know the initial data f and g, so the solution is given by this nice formula. And if we want to see this graphical geometrically, so what we have here, we have a hyperbolic equation. So we have two families of characteristics. These are the lines x minus ct equal to a constant and x plus ct is equal to a constant. And so if we are in the upper half plane and we are at this point A with coordinates xt, then in order to find the solution of this initial value problem at the point A here, what we have to do, we have to draw the backward characteristics, see the points A and B which intersect the x-axis, and then rewrite the solution in this form. The solution at the point A in the upper half plane is the initial position at the point A plus the initial position at the point B plus the integral of the initial velocity of this interval from A to B. So this formula down here. This, of course, is nothing else but a geometric interpretation of the formula of, which was derived by D'Alembert, but there is a nice consequence of this formula, which is known as the parallelogram relation, which says the following. If we take four characteristics of the wave equation, like these four lines which are shown here, and then consider the points of their intersections, these points A, B, C, and D, then the D'Alembert formula simply says that the value of the solution at the point A plus the value of the solution at the point C is equal to the value of the solution at the point B plus the solution at the point D. So this relation here. And this is just a consequence of that formula, of the D'Alembert formula. The nice thing now is we can interpret this equation here in this graph as a two-dimensional lattice. Right, so what we can think, let me just for one moment switch to my blackboard. Right, so, oh, sorry, that should be here. Right, so let me just use, now let me do it like this, so we can think the same graph in this form, where here is the point, well, let's say this is A, this is B, C, and D. So we can say that point A corresponds at the point with coordinates n, m, and the z-squared lattice. The point B corresponds to the point with coordinates n plus 1, m. In the same way, D is the n plus 1 point, and C is n plus 1, m plus 1. And then we can say that the value at the point A is u at the point n, m, plus the value at the point C, u at the n plus 1, m plus 1. And this is equal to the value of the solution u at the point D. Oops, sorry. Plus the value of the point B. Oops. And this is exactly a difference equation, a partial difference equation, which is this one here. So starting from something that we know from the wave equation and a nice property which follows from the solution of the initial value problem, we can write down this nice equation, which is actually referred to as a discrete wave equation. And in fact, we can derive the same equation by discretizing the wave equation in null coordinates. And this is a linear difference equation, linear partial difference equation, right? And we can write down the general solution. And of course, since this has the name, this is a discretization of the wave equation in null coordinates, the solution is a sum of two functions, one depending on n and the other depending only on n. So this is an example of equation that I'm going to think, and another example that we have from of this kind of equations comes from integrable systems and vector transformations for the potential KdV equation. Right, so here we have the potential KdV equation, and it is known that this goes back to the work of Wahlquist Estabrook, who actually constructed this Bernoulli transformation back in '73. This is the reference here. And if U is a solution of this equation of the potential KdV, then U tilde is a new solution of the same equation, which is determined by this relation here. Right, and here this K is a parameter, is a real number, right? And now what we can do, we can start with a solution of the potential KdV equation. We can just start with a constant solution and then use this Bernoulli transformation to find two new solutions, U1 and U2, according to this diagram. So I'm starting from U. I'm using my Bernoulli transformation here with parameter K1, and I derive a solution U1. I can do the same thing starting with U, the Bernoulli transformation, but now with parameter K2 to find a new solution U2. Right? Then I can require this diagram here to be commutative. So I require this. So I require to start from U1, my Bernoulli transformation with parameter K2 to derive solution U12, which must be the same if I have started with U2, Bernoulli transformation with parameter K1. And then this solution U12 actually is, we don't have to integrate anything. We don't have to solve any differential equation. Is given algebraically by this solution here, down here. And this is the superposition principle of this Bernoulli transformation. And again, as I've done with a wave equation, we can think this diagram in exactly the same way, that we have a lattice here, and U1, U2, and U12 express the shift of my function, this, or the values of my function in these 4 points. So I can just rewrite this equation in this form. Interestingly enough, this equation was derived actually in a completely different context by Frank Neyhoff, Reinhard Quispel, and Hans Capel in '83, 10 years later, in the context of direct linearization, where they have a very nice machinery to produce integrable equations, differential difference equations. So in this context, they derive the same equation as a fully discrete equation, also as a partial difference equation, and this is referred to as discrete potential KdV. And actually, they have shown that this integrable difference equation, because it has Lax pair, it is 3D consistent, it admits Solton solutions, and it has infinite hierarchies of symmetries. And all of these things and more other properties, nice properties, this equation has. Okay, so this kind of equations I'm going to consider for most of my talk, and just to give a general description of this class. So what I'm going to use as the class of equations here is equations which involve exactly these 4 shifts of U, of 3 values of U. The function Q, which defines my equation, depends on U at the point n, m, n plus 1, m, n plus 1, and n plus 1, n plus 1. So on this elementary quadrilateral of the lattice. That's why sometimes we refer to this equation as quad equations. And now for this equation Q, for this equation here, this defining polynomial, this defining function Q, we require 2 things: to depend on these 4 values of U explicitly and linearly. Well, explicitly means that all these derivatives of Q are not 0. And linearly means that the second derivatives of Q, all of them are 0. Okay, so that these 2 equations that I've shown you, the wave equation, the discrete potential KdV equation, are exactly of this form, of this form. And some other equations that are these are the 2 equations that I've already shown you. The other 3 equations which are really important, I'm going to say Rotegi equation, which is written, well, it's not the standard form that we see Kurota's KdV equation. So, but if you write it as in polynomial form, this is the equation, right? Again, it's a quadrilateral equation. This is the equation that I've told you earlier, which comes from my paper with Sasha back in 2013. This is again a nice quadrilateral equation, and Adler's equation, which I think it was in 2011 or 12, which is called the Cheika equation, is actually can be seen as a deformation of the equation that we derived with Sasha. So these kind of equations I'm going to discuss in what follows. All right. So in order to discuss more about integrability and of course symmetries and operators, all these things, I have just to do some further notation. Right. So now, since we are talking about discrete equations, difference equations, we don't have differential operators, but we have shift operators. So we have two shift operators, one in the n direction and one in the m direction. So what these two operators do is when it says n, change it, shift it by this index l, and t, shift m by this index l. All right. But we have to keep in mind these are not derivations. They are not. There is no Leibniz rule. So when we shift a product of two functions, we have to shift. We just have the product of the shifts of these two functions, and they commute. Right. So these are the shift operators and their properties. Just a few examples here and some notation that I'm going to be using in order sometimes to avoid to write all the arguments of a function f. So I will use this notation here to denote the dependence of f on u, right? And a finite, but otherwise unspecified number of shifted values of u. So for instance, if f of u could be something like this, and here are some examples of how these operators, these shift operators, act on this function. So when I act with s minus 1 on this function f, what I'm doing, I'm just shifting n by minus 1. I just subtract 1 from n everywhere here in all these indices. So that will become n minus 1, that will become n minus 2, and here n will become n minus 1, and so on. The same with t and the combination here as t. Right? This is a nice notation because I'm going to use it in a moment when I will define with operators, guess patterns, and so on. Right. So in order to start, before talking about saying about a few things about symmetries and the guess patterns, let me, as I've said, there is no universal definition of integrability. There's a plethora of tests and criteria. I've mentioned already lax pairs. This is really useful to solve the initial value problem and construct solutions. Background transformations, like the one that we saw earlier for the potential KDV, transformations which map solutions to solutions. Another interesting property which can be used as a criteria for integrability is multidimensional consistency, and this was introduced by Frank Neyhoff, and later it was used as integrability criteria for the classification of integrable cases. Of course, solid on solutions, as we know, is an indication of integrability of an equation. The existence of hierarchies of symmetry conservation laws is another integrability test, another criteria for integrability, and this is that I'm going to discuss in a moment. Reduction to discrete Painlevé equations is another indication of integrability. There are also similarity confinement with break entropy, which is something equivalent to the Painlevé test, right? Needless to say, of course, that the best test is this one. Okay, so let me just then start introducing the concept of symmetry and then move on. So,
Pavlos,
what is
it? Something?
Yes.
You said that you will be focusing on the difference equations that where the Q is multilinear.
Yeah.
Well, I understand multilinearity is essential for Frank's 3D consistency. Is it also needed for your symmetry definition?
It is necessary when you want to prove things when you want to eliminate variables.
I see.
I will explain in one moment. I will say yes, but in general, you can prove steady consistent. That I think that was also in a paper by James Atkinson, where they with the sports where they discussed this quadratic equations which are quadratic, and they've shown that they are 3D consistent. So yes, depending on the equation, but yes, let's keep it simple for my computations. I need my equation to be uniquely solvable with respect to these four variables. Okay.
Yeah. Thanks.
Right. So what's a symmetry? Symmetry is a transformation which maps solutions to solutions, or is a transformation which leaves the equation invariant. Right. In order to introduce it, and again, because it is just asked me to make it a bit introductory, sort of. So I will just start by considering a simple point transformation. What is this? This is a transformation. So I have an equation. I have my function u, right, and then I construct a new function u tilde, which is given in terms of the previous function u on the independent variables n and m, and here on a continuous parameter epsilon. So I have what I have here is one parameter group of transformations, and here I assume this transformation T is a smooth function of u, and also it's an analytic function of epsilon. This is quite useful in a moment, because at some point I will need to take some Taylor expansion. Right, so this kind of transformation, they form an additive group, and the identity corresponds to epsilon equals 0, right? So what does it mean? So I have this transformation. So now I can, once I have this transformation, I know how all the other values of u change. So if I just shift this transformation, I can find how the u tilde at n plus I, n plus j is. It's just the shift of this transformation in both directions, right? So whenever I have a transformation, I want to transform all the other values of u, I just shift using my operators s and t. Okay, so I have the equation. If I assume that this is a point, is a symmetry of my equation, that means the equation, these new variables should remain the same, as this definition here suggests. The equation remains invariant, right? So that means if I have this transformation is a symmetry, then the equation should keep the same form. Okay, so here my equation should be independent of epsilon. So now what I'm doing, I'm just going to take a Taylor expansion. I do it in a way just to my physicist friends will not be complaining. I will take the actual Taylor expansion. So that means I will take the expansion about epsilon 0, and I will keep only the first term. So I will keep only this. Okay, if I do that, so I will end up with this expression here. Here now, this q is the one here, because everything is evaluated at epsilon 0, and when epsilon is 0, we've said that the transformation is the identity. So u tilde will be equal to u when epsilon is 0. So I have this relation here, which says that I have a sum. Here the sum is finite, depending on the number of shifts of u involved in q, and I just multiply these derivatives by the shift of my shift of this quantity f, which is nothing else but the derivative of my transformation with respect to epsilon evaluated at epsilon 0. This is what we call the symmetry generator, or simply the symmetry. And this is the most interesting relation here about symmetries. And just to give you an example here, well, I'm just going to use for as a running example the discrete potential KdV equation now written in this form, right? For this equation, there are 3 points. Well, what I call here this kind of symmetries, which this symmetry generate with 3 symmetry generators. One, this is equal to 1. The other one is -1 to n plus m. The other is this one. And in order to prove that, what we have to do, we have to just take, let me just go back for one moment. We have to take this expression here, right? So what we have to do, we have to differentiate this with respect to u, and this is the result, and multiply it by the corresponding symmetry generator, plus this is the derivative of my equation here with respect to un plus 1m. This is the derivative. And I multiply this with the shift of my symmetry generator in n, and so on and so forth. And then I add all these terms, and that must be equal to 0. Of course, this must be in general on solutions of the equation. Right, and here is actually related to what Sotir was asking. So let me just switch again to my blackboard for one moment. Right, so what I want to do now, I want to use my equation. My equation is defined here to show that the expression that I got is equal to 0 whenever u satisfies this equation. So I want to be able to solve this equation for any of these 4 values of u. So that's why I require my q to depend linearly or on these 4 values. So for this elimination, I have to solve my q. Let me use this example here. Right, I can solve here for un plus 1 and n plus 1, and that will be un m plus 1 plus un plus 1 m minus un comma m. And so I can use this relation now to replace un n plus 1 wherever it appears in this equation here, if it appears at the end, right? And so on. So that's why I require these equations to can be solved uniquely with respect to these values. And in the case, of course, of this kind of transformation that I've discussed here, these simple transformations or point transformations, actually, I can also go back from the symmetry generator and construct the symmetry transformations, but this is not important in this case. The most important thing here is just this relation here.
Pavlos, but I
Yes,
think that Sotiris' questions was absolutely correct. You don't need all angles to be solved to do elimination. You need half, 2 of them only.
Yes, true, indeed. But in order, but then the discussion will go on. Just to simplify things. I will come back to that later when I will discuss systems. Right, so that there is that will be clear. Right, so the most, as I was saying, the most interesting relation is this one here, and that will be actually now we will try to generalize to discuss to generalize and discuss more higher order symmetries. Okay, so that last relation does not depend on the group parameter, so which is quite essential. So this involves only our function u and the equation and the symmetry generator, which also does not depend on any parameters, on the group parameter. Right, so what we can do now, we can just take this relation. We can allow now our symmetry generator to depend not only on u, but also on shifts of u, on unspecified but otherwise finite number of shifts of u. And then we can give the following definition. A function f which depends in general on n, m, and a number of shifts of u is a symmetry generator, again, simply a symmetry of our equation. And this is a general definition, right? If this relation holds on solution of my equation. And here I've just used this notation dq, which is the first derivative. It's again this quantity, this operator, which appeared earlier. And I'm going to say a few things about this in a moment. Just some extra terminology. I've mentioned already in the previous example that when f depends only on u, that this is a point symmetry. In any other case, when f depends on most shifts, then this is a generalized. Okay, so the criterion for a function to be a symmetry is this one here, and this is that I'm going to use from now on. And for this first derivative, right, this is a linear difference operator. And of course, as I said earlier, this contains a finite number of terms. For the equation that I'm discussing, we are considering here, remember that the equation q, oops, this is Okay, depends on u n m un, and then yeah, this is 2. Right, so this function here depends only on these 4 values. So we have only 4 terms in this percent derivative, right? And now we can factorize the different ways, and this is crucial because this is what we are going to use in a moment. We can factorize in this way, right? So what I can do, I can keep these 2 terms together, and this is what I call operator A down here, right? And then from these 2 terms, I can take t, the shift operator in the second direction, operator t, as a common factor on the right, and then have the operator b here. And this is here. And actually, because I'm going to discuss only symmetries in one direction, so, I'm going to use this one. So the other one is when I do the other way around, I keep this term, these 2 terms together, right? And this is my operator C. And then from this term here and that term there, I take S as the shift operator in the 2 directions a common factor, and I have this guy here, right? But again, I'm just going to focus on this factorization. All right, so as I've said, for integrability, what we need not just one generalized symmetry, but we need an before that, let me say a few things that about the equation and the elimination. Now, for these quadrilateral equations, and according to the linearity that we've said, conditioned on function q, we can use the equation to eliminate all these kind of shifts, where k and l are integers, non-zero, both of them not zero, right? And just to explain how, right? So if I'm just draw a few lines. So if I have my equation here, right? So what I can do, I can solve now with respect, let me just distinguish these 2 lines here and there. Right, I can solve now my equation with respect to this value, and then if I do that, I can use it to eliminate also this value here by shifting the equation, or this value here by shifting the equation in this direction, and then this by shifting the equation twice. So I can eliminate all these values by just using my function q, my equation q, and it shifts. In the same way, I can then solve my equation with this. I can use the s-1 equation here to eliminate this value, and then I can start shifting and eliminate all these values here and there. And in the same way, I can eliminate this, and that. And so at the end of the day, I can eliminate all the values here and just keep the variables with indices n plus k comma m, and on this line, and all the variables here, right? And so that means that generalized symmetry and conservation that I'm going to discuss in a moment will depend only on these variables, because I can always do that because of my assumptions on function q and the elimination of these variables modulo my equation. For this kind of equations, another important thing is that we can always, even though the equations in general depend, the symmetries in general depend on both of these set of variables, actually, generalized symmetries always split in this way on a cross. We have one part which involves shifts in one direction. So if I go back, so involves only the shifts on this horizontal line, and then plus a function which involves shifts only this vertical line. And this is the horizontal part, if you want, and this is the vertical part. And always it's symmetric with respect to these ends here, these shifts here, which appear. Right, so again, because I'm going to focus only discussing symmetries in the n direction, I'm going to discuss symmetries of this form, where this number n, this positive integer, which is greater or equal to 1, is the order of the symmetry. So from now on, I'm just going to consider only symmetries of this form. Okay, and I've said it already, I'll say it again, we need a hierarchy of such symmetries of increasing orders. And to construct such a hierarchy, what we need a recursion operator. What is that? Is an operator, a pseudo-difference operator, right? Which maps symmetries to symmetries. For instance, this is an example of such an operator, and this is pseudo-difference because of this term here. We have the inverse of a linear operator. All right, so what we have to do, if f is a symmetry of our equation, then we act with our operator R on the symmetry. And if this is well defined, then this R of f is another symmetry of the equation. This is the notion of the operator. I take a symmetry, I act on my symmetry with my recursion operator, and I get another symmetry. And how I can show that if a given operator is a recursion operator? Well, there is this theorem which says that if there are two operators R and P which satisfy, and dq is the first derivative of my equation, right, of the defining function of my equation, and this relation, and they satisfy this relation here, then R is a recursion operator of the difference equation Q equal to 0. And actually, this is the key relation here. That is the relation that we're going to exploit and derive all the integrability conditions that I've said.
Can I ask if there is a recipe for constructing this recursion operator if you have at your disposal a number of symmetries?
Well, in order to construct the recursion operator, you need some symmetries, and you need a few elements of the symmetry, and then you have to ask Jinping to tell you the secret. This operator here was derived by Jinping, so she knows better than me.
Okay.
Okay, yeah, definitely there is a way to do that. Right, so for these equations that we are discussing, we said that the first derivative is factorized in this form, like with a using these linear operators A and B, right? So, and here are these two operators, linear operators. And if I start with this relation here, the definition from the theorem previously, right? And this form of the first derivative, this factorization, and then this relation here leads to this result. So here on the left side, I just shift the entries, the functions which appear on my recursion operator. On the right-hand side, I have this composition of operators. The only disadvantage with this one that it involves the inverse of linear difference operator, like this one and that one, and also a pseudo-difference operator like this one, which, well, we don't know, right? This is what we want to find in some sense. Right, so instead of using this relation as it is, what we can do, we can just replace all the operators here with some formal series, with their formal series. Right, so because this is easier to manipulate, and when I'm saying formal series, I mean something like this. Formal Laurent series. So if I have s-1 to s-1 to minus the inverse of this operator, I can represent it formally with this infinite sum of negative powers of s. Or I can use formal Taylor series, which, like this example here suggests, which involves an infinite number of non-negative powers of s. Okay, and in general, for an operator like this, A and B here are some functions which depend on n and m in general. The formal Laurent series of its inverse can be written like this, where P1 is the shift -1 of 1 over A is the coefficient here, And then we can move on and find P2, and there's a nice recursive relation for all these things. Or we can use the corresponding Taylor series, right? So we can represent this inverse as a formal sum of positive and non-negative powers of S, like this one, which starts with this Q node is 1 over B, this constant here, and so on. And now what we can do, we can just go to this relation, the defining relation, if you want, of the regression operator, substitute A and B and the inverse of these operators with their formal series, either Laurent or Taylor. We can assume that regression operator has some order. Here, I forgot to mention that this is a first order operator, right? Because it involves S power 1. So the order is the highest power of S appearing in the operator. So what we can do, we can assume that S is, or this R is of order n. So we can replace a formal, we can replace R with a formal Laurent series here, A and the inverses of A and B in the same way, and then we have some series on both sides, and then we just compare terms. And this set of conditions that we will get is what we call integrability conditions for the equation Q equal to 0. And just to give you an idea of how these relations look, here is when we assume that our recursion operator is of order n, right? This is, again, here is a Laurent formal series. It contains a finite number of positive powers of S, right? Non-negative powers of S, and then an infinite part of negative powers of S. And this is a formal Laurent series for the regression operator. Then for A and B and the equation we have, we can determine all these operators which appear on the right-hand side, and we can collect in terms and write them down in this form. This is the first n+1 conditions which follow when we are using the Laurent series, the formal Laurent series. Again, all these alphas and betas are given in terms of the function Q, which defines our equation and its derivatives. And the unknowns are the coefficients of our operator R. So these guys here are Rn -1, -2, up to R0.
Can I add something?
Yes.
Sorry for interrupting. So I understand that you cannot obviously work with inverse S-1. So you take infinite Laurent series and you substitute, etc. So the result of this procedure would either give you symmetries or conservation laws, etc. The question is
both.
Yeah, but okay, both. Yeah. So the question is, well, in practice, you don't use infinite series. You use a finite.
Yes, and what I'm going to say in a moment, actually, in order to find symmetries, you need only these terms, the first n terms here. If you want conservation laws, right, you will need also to get this one, and if you want something more, you have to compute some extra terms on here, some negative terms. But in order to find conservation for symmetries, we need only these. If you want to find conservation laws, you have to compute as many as possible.
So no, my question is, since even if you use a finite number, you still assume convergence of this.
No, we don't. That's why I accept formal series. Convergence is not involved, but everything is formal. No. Right. And since Xenitidis are so, the first relations here, these first n relations, involve only these coefficients, the first n coefficients of my recursion operator only. And actually, this well, here is written with logarithms, but actually you don't. You can write it. You can exponentiate, get rid of. Actually, what we have here is a linear system for these coefficients. And this is important because this system actually will give us, is part of the determining equation for the symmetry of the equation. The other, and I will come back to that later. The other important thing that, and it's highlighted here, red is this equation, the first of the integrability condition here and this one. Both of them have the form of a conservation law. And let me just explain what is a conservation law. A pair of functions rho and sigma is a conservation law of my equation if this relation holds, again, on solution of the equation. And just to use a terminology, that rho usually is referred to as conserved density and sigma is the corresponding flux. Probably this is not the best terminology in this case, but nevertheless, a little bit standard terminology. And so, if I go just back again, this is a conservation law, and this is another one. So these integrability conditions already provide me with three conservation laws for my equation. And these two conservation laws are actually related to the so-called residues of the recursion operator. And what is a residue? So if I have a Lorentz series, a formal Lorentz series like this, right? The residue and the logarithmic residue are defined like this. The residue is the constant term, and the logarithmic residue is the logarithm of the leading term of this series. So these two quantities here. And I hope this is exactly clear here. So this Rn, this is the leading term and appears here, right? And the right-hand side is completely determined by the equation. So this is a conservation law for my equation, right? And the last relation down here involves the constant term. This is the residue of this operator. And this relation, this integrability condition, has the form of a conservation law again. And in fact, not only that, but if you take the powers of the recursion operator, so you start composing R with itself and take the residue, not the logarithmic residue, but just the residue, then you can derive higher and higher order conservation law. And for this composition and for these compositions and derive the conserved densities and the corresponding fluxes, you need, of course, as many as possible terms in your Lorentz series, in your recursion operator. So in that sense, you need to, as I told you earlier, you have to go with as many as possible terms in this series. But just to show you an example of how all these things work, I'm going to use again. Before that, yeah, as I said earlier, and I mentioned that these relations here involve only the first n terms and coefficient of the recursion operator, and actually they are related. They can be used to determine the symmetries of the equation, right? And why is that? Because actually the Lorentz series of my recursion operator actually can, if f is the corresponding symmetry of order n, then the Lorentz series of R will be of this form. The first n terms of my Lorentz series will involve the derivative of my function of my symmetry f with respect to the shifts of f with respect to un plus 1 comma m, un plus capital N comma m. And if I use Taylor series now have a finite part which involves negative powers of s, and then an infinite part of positive powers of s. And now the negative, this finite part, which involves the negative powers of the shift operator, involves the derivatives of my symmetry with respect to the backward shifts of my function u in the n direction. So involves u, a derivative of f with respect to un minus 1 comma m, and so on and so forth, and the derivative of f with respect to u n minus capital N comma m. Right, so I can just use these determining equations coming from Lorentz and Taylor series to find all these derivatives of my symmetry. Along, of course, with the very definition of symmetry, that the first derivative of f in the direction of q is equal to 0. So all these, the first integrability condition from the Lorentz series, the first integrability condition from the Taylor series, and the definition of the symmetry are determining equations for the symmetry F. And this is a linear system of functional equations. And this is the most important thing, this is a linear system. The difficult bit is functional equations. And this system, in fact, can determine the system which comes from the integrability condition and would determine the function F, the symmetry, up to an arbitrary function of u only, which then can be determined by using this equation here. And even though the regression operator may not depend on the independent variables, this procedure here will give us all the symmetries of the equation of order n, including the ones which depend explicitly on the independent variables. And because we don't know beforehand the order of the regression operator, we have to start with order 1. And then if we don't find anything, we move on to go to order 2 and so on and so forth. And here is the example that I've used again, the potential KdV equation. Right, so here what I'm doing, I'm just checking for symmetries of order 1. That means symmetries which have exactly this form. Right, using the integrability conditions, I have these two equations here for the first order derivatives of my symmetry F, plus, of course, the equation, the determining equation of the symmetry. So, of course, in this case, we start by solving this system, because this involves just one function, the derivative of F here with respect to this shift of u, and its shift. So just one function. Here, this one involves one function, but shifted in three different ways. Here, here, and here. Right. So let me just switch to my blackboard again. So what I have here is that I have the shift of, okay, instead of writing f with some index, I'll just use f. And I'm just dropping the dependence on m just to save some time. So here I have a coefficient a, and then I have okay, so here I have, this is the equation. Here, this coefficient a, well, this guy here, which I don't want to write again, right? But so here I have my function h, my unknown, with two set of variables. Right? H is here. Here, this is u at n, comma m, or un. This is un plus 1. This is un minus 1. And here h is not only these three values. And here the right-hand side, sorry, the left-hand side involves these three shifts, because I have to shift it in a t direction. So I involve now this. So here I have t of 8, and here I have 8. But all these values, all these shifts are not independent, right? Remember that this relation must hold on my equation. So I have to remember that q is equal to 0, which lives here. And here I have shift minus 1 of q. So I can use these two equations to relate these two different sets of variables, the brown ones and the yellow ones. And I can do it in two different ways. And I don't have the time to go through all the details now. But the good thing is that I can exactly use this fact that all these variables are related through my equation. So I can eliminate in one case one set of variables or the other set of variables, and this can help me to split these two equations in a system of partial differential equation for this unknown function. So, oops, sorry. So for the first integrability condition, which involves this derivative of f, now I'm just calling it a tilde just to save some space. From that equation that I've shown you on the previous page, I derived this system of first order partial differential equation. And from the second equation, which involves the derivative of my symmetry with respect to un minus 1, comma m, so which I call now r hat, I find this system of partial differential equation. And these are very nice system of first order partial differential equation. And the nice thing is that all this procedure, which can bring me down to this equation, can be easily programmed and done using mathematics. All right. So now I can solve these equations. I can determine the partial derivatives of my symmetry with respect to un plus 1 and un minus 1. Right. This system will determine f. Now these two equations will determine f up to a function of u comma m, which then is determined by the determining equation of my symmetry. Right. At the end of the day, all this procedure will give me this answer.
Can I ask a little bit on something on the notation? So
Yep.
R tilde is f within.
No, this is just a shorthand notation for this function. And
Yeah,
hat is
but
just
then what means R tilde with index in the first equation?
This is a partial derivative. Sorry. Yeah, like yeah, this is the partial derivative of this function of r hat with respect to un plus 1 comma.
Yeah, got it. So now understand the notation. Yeah, thanks.
Right, so these two sets of linear first order linear partial differential equation determine the derivatives of my symmetry. Then I can find find the dependence of my symmetry on these shifts of u, and then the dependence on the function u comes from here. At the end of the day, I find these symmetries. Right here, what I found actually is not just one, but 5 symmetries, because here I have 5 constants, C1, C2, and C3 from here, and then alpha and beta, which are hidden in this function, which I used here, which involves only n. So I have 5 symmetries in total. These 3, which corresponds to these 3 constants here, are the point symmetries that I've shown you earlier. And then taking alpha 0 and beta 1, or the other way around, I have to generalize higher order symmetries. And here is these symmetries, right? This is the first symmetry, the first generalized symmetry, G1, and this is the other one, which depends explicitly on n. And now for this one, we have also the recursion operator. So what I can do, I can just take R and act on this G1 to find a new symmetry. And that will give me a new higher order symmetry of second order, which means that will involve shifts from un minus 2 comma up to un plus 2 comma m, right? And these are all in that sense local symmetries. This one here, because here my symmetry depends on n explicitly, this action will result to something that I cannot, let me put it this way, I cannot integrate it directly, so I have to introduce a potential, so that will use me some non-local symmetries. But they can be these. Let me just show you how this first symmetry, these symmetries go. So if I start with G1, then G2 is G1 squared, and then we have shift of G1 plus shift minus 1 of G1. And this is how I can write my second symmetry. For M1, then if I apply my operator, I will get M2, which is actually n times my symmetry G2, which is here, this one. Then I have plus my symmetry G1 times a function phi. And here I have minus u and comma m divided by 2k1, sorry, that should be plus now, minus k2 squared. And this phi here, this potential, actually is such that, sorry, this is the first conservation law that follows from the integrability condition that I showed you earlier. And actually, it's also on my next slide. So in this case, in that sense, because I have this term here, which I cannot integrate, I cannot solve this equation and express phi, this potential in terms of u at its shift. So it's a non-local symmetry. And this, in order to find the conserved density and conservation laws, what I have to do, I have just to take my formal recursion operator. Right here, I use this shorthand notation for this guy. In this case, because I have the recursion operator, I can just write down the whole series. This is the formal series of the recursion operator. This is the leading term. So, and this coefficient here gives me, the logarithm of that gives me one conserved density. The constant term here gives me another conserved density. Then I can take, and this is this rho 1, which appears in the potential that I've shown you earlier. And then I can take r squared and find again the constant term in this r squared, and this is the form, the result of this operation, the constant term of the r squared operator. And of course, the corresponding fluxes can be found by using just the integrability condition, because they will come for free from there. All right. So, okay, so we found symmetries. They are useful to prove integrability in that sense because they give rise to this integrability condition. From there, we find conservation law, and so on and so forth and so forth. But we can also use them to find particular solutions, right? So, seeking for particular solutions, usually we are led to lower order difference equations. One way to find particular solution is what we call periodic reduction. This is a discrete analog of traveling wave solution. So what we do, we just seek for solutions of this particular form. Or in other ways, we want to solve our equation accompanied by this constraint. Well, this constraint is easy to solve. It's exactly this guy here. And then we substitute back into the equation that we try to determine this phi. And this, of course, will result to a map, to a first order, to an ordinary difference equation. From the other hand, what we can do, we can use the symmetries to find the group invariant solutions, right? And how we can find them, what we do, we just take the symmetry generator, these functions f that I've shown you, set them equal to 0, and solve them along with the equation. And this usually leads to discrete Painlevé equations, right? And for the KdV equations, the discrete potential KdV equation, here these several symmetry reductions and periodic reductions have been studied. Probably this is the first equation to be studied from this group invariant solution, this kind of reductions by Frank and Vassil Papageorgiou back in, if I'm not mistaken, late 80s, early 90s. So this is well-studied equation from this point of view, but all these symmetry reductions involve only the symmetries which are local, like this G1 that I've shown you earlier. There are also the non-local symmetries, one which like this M2, right? And in this case, we can think about solutions of the KdV equation, which remain invariant under this symmetry. And in this case, what we end up with is a third order non-autonomous ordinary difference equation, which probably, I'm not sure, so this is something a work in progress, corresponds to higher order discrete Painlevé equation. So in this case, when I just consider my KdV equation along with my second order non-local symmetry M2 that I showed earlier, then this system will lead to these two equations. This, the second equation is for the potential phi. The first equation for x is for actually the x which appears already in I showed you earlier. It's, let me just, well, in some sense, it's actually the inverse of that. Actually, is this denominator in this case? Yeah. So this, and as far as I'm aware, this is something new. Not, I haven't seen such equations arising from this kind of reduction for partial difference equations. And but anyway, this is something that some work in progress at the moment. So this is one of the uses of symmetries to derive this kind of solutions. The other interesting use of integrability conditions is that can be used for classify integrable equations. And this is a really challenging problem. It's really difficult. It's not an easy task. Probably for evolution type partial differential equations and systems thereof, the symmetry approach probably is the most fruitful method to provide and have provided us with a list of integrable equations. And I've seen here is Vladimir, Sasha, Jiping. They can say a lot about this subject. For differential difference equation, the same approach was used by Yamilov to classify Volterra type equations and other types of equations. That was back in the 1980s. And there is an eye review paper in JPhys A, in Journal of Physics A, where he described all these classifications. More recent results appear for second order equation, again from Yamilov and Korwalk, and also from Adler. So this kind of approach was used for differential equations, differential difference equations. For difference equations, there is only one classification result by Adler, Bobenko, and Schmitz, which is actually based on the notion of multidimensional consistency. And using the symmetry approach, there was some results by Yamilov and co-workers, and which they've used the symmetry approach. When we were working on the second order integrability conditions with us, and we derived the second order equation that I've shown you, actually there was a small classification behind that equation. That that time what I considered was this family of equations, right? So here is again equation in this class that I'm discussing so far, but I require my equation to involve only terms. Let me just go here. Either terms u or u or triples or ux. So if I have q of u, x, y, z, so in general I require that to be of a4, a31 u x y plus a32 u x z, and so all these kind of triple products, and then a11 u plus a12 x, so the single terms and the constant term I know. So I have all these terms involved, and then I require some symmetry conditions. I require my function q, the equation to be invariant if I interchange x and y, or if I interchange u and z, and all these things boils down to this kind of equations. And then just using the integrability conditions to distinguish, to find the integrable case from the not integrable ones, then this analysis leads to actually 4 cases. Let me just skip to that. Right, these 4 equations. The first 3 equations admit symmetries, the lowest order of which is 1. Right, so they have symmetries of order 1, 2, and so on. In the first equation, alpha is a real parameter. If it is not 0, we can easily set it equal to 1, and beta is a constant, is a non-zero constant. Right? If it is 0, the equation is linearizable. So I can just transform it to a linear equation, and I'm not interested in linear equations. The second equation here is alpha is different. It cannot be 1. If it is 1, then it is linearizable. right? Because actually it's the first one. And actually this is for alpha equal to 0, this is the chaotic KDV. Then the third equation involves a parameter alpha, which cannot be 0 or 1. If it is 0, it's not a quadrilateral equation. If it is equal to 1, it's linearized. And finally, the fourth equation is the equation that appeared in that paper with Sasha Beck in 2013, which admits symmetries of second order. And this is actually one of the two first examples of equations admitting symmetries of order 2 and not of order 1. This was the second one, and the other one is Adler's equation, which I've shown you earlier. And this is Adler's equation, which actually is a deformation of this equation. So we can combine this equation here to derive. We can use this equation to derive the Adler's equation in a systematic way. Okay, so far I've just considered all the equations which defined on this elementary quadrilateral. I can, of course, if we discuss only this kind of equations, it's not very interesting. So the thing is to consider extensions. This theory can be easily extended to equations which are defined on D consecutive quadrilaterals. So now I am on the lattice and I have an equation which is defined here, right? So it involves all the values of U on this, well, the values of U on this line plus the values of U on this line. And here, what I require is my equation to be linear, so I can solve it uniquely with respect to these 4 corner values only. I don't care about the values in between. But I require also to depend essentially on these values, the intermediate values, so that it cannot be reduced to something smaller, right? So roughly this is what these two conditions say. And one equation which of this form, which I think I forgot to write. So, well, I can just give you a constructive way for that. So let's take, this is n plus 1, n plus 2, m. Here I have n plus 1, n plus 1, n plus 1, and here I have n plus 2, n plus 1. So I want to start from here and go there and find all the path by moving either right or up. So I can go in this way, so this one path, and with this path I associate the product u at n, and u at n plus 1, and u at n plus 2, n. Right, then another path is if I go from here, there, then up, and then there, and with this, and this, of course, I associate, I forgot this, and with this path, I associate this product, the product of the values of E at these vertices, right, and then the last path is this one, and then there, and with this one, I can associate and if I call this equal to a constant alpha dot 0, then this is an integrable equation of this kind, which is defined the two quadrilaterals, right? And for this kind of equations, I can easily find the symmetries in the n direction, simply because this is an extension of the theory that I've discussed. In this case, the only difference is that the operators which are involved, that percent derivative, are of order d, right? D is the number of that quadrilaterals involved here, and so the Lorentz series start from h to d minus 1, but the Taylor series start always from the constant term. This is the only difference. This is for the symmetries in the n direction. For the m direction, for the vertical direction, however, it's more convenient to write this as a system defined on an elementary quadrilateral and study the system, the symmetries of the system. And this can be done, and I mean, there is this theory can be easily extended to systems. So here, what we have a system of d equations which involve the function. Well, here is a vector U, with D components, right? And so here a function or F is a generator of my system if this relation holds on solution of the system. Here we have now these matrices. We have 4 D by D matrices, which just involve the partial derivatives of the function of the equations of the system with respect to the shifts of the functions involved in the system. Right, and so this is the same definition, and we can work in exactly the same way. We can assume that there is a recursion operator which maps symmetries to symmetries, and the condition is exactly the same. And this is the equation that we have to use. Where now, of course, this A and B are the matrices that I've shown you earlier. Right here, these Q nodes, not Q1 node, are these matrices here, the ends of which are determined by these relations, right? And now, of course, we have to take it then to replace everything with formal series and find and try then to replace these inverse operators with a formal series. And here the things become a little bit more complicated simply because these matrices here can be non-invertible. Even in this case, we can still work this equation. We can write down the Lorentz series or the Taylor series for these operators, even though the matrices involved are not invertible. And there is some interesting development in this direction. Well, probably not time to say anything today. Probably that will be for another seminar. But again, this theory can be extended in this direction. Of course, needless to say, if all these matrices are invertible, everything works exactly as in the scalar case. But when these matrices are not invertible, then we must be a little bit careful about how we write these inverses here, the formal series for these inverse matrices. Okay, so let me just summarize of what I've said. The integrability conditions, of course, the main property of these conditions is that they can be used to prove, to check the integrability of a given system of difference equations. But the interesting thing is that they can be used to determine, to find the symmetry of the equation, not only just conservation laws. And of course, for the scalar case and also for the matrix case, all these conditions can be formulated algebraically, so we can use them in symbolic computation, so we can write them as a nice program for mathematics and do all these computations. And even though I didn't mention it, but I hope that it's clear that actually all these determinate equations can be used for non-autonomous equations as well, right? And but in this case, of course, the computation could be more complicated. And of course, other uses for classification and solutions which are related to discrete Painlevé equations. But maybe the most interesting thing here is how to extend this theory to difference equation defined on different stencils. Here, I've just stencil, I mean where this equation is defined. Here, I'm just using quadrilateral. So what happens if the equation is defined on some other involves not, for instance, if my equation is determined on a configuration like this. Right? Can we write down the integrability codes for a system for an equation like this? Well, for this particular one, the answer is yes, we can do that because we can relate as a quadrilateral system. But you understand what I want to say, that how we can just extend this theory to include more equations in this theory. I think that's all I had to say. Thank you very much.
Okay, thanks very much, Pavlos. Are there any questions or remarks? I think Yorgos wants to ask something.
Hi, Pavlos.
Hi, Frank.
This is Frank. Let me start the video.
Yes.
Very nice talk. I have a question about this result that you had on this kind of Painlevé reduction for the potential KdV.
Right. Let me just go back to that page.
Yeah, go back to that.
Yes, here it is.
I'm just wondering, our approach with Vasilis at the time was to look at similarity reductions on the lattice, which kind of incorporates scaling symmetries. This is quite a different approach. So is there any kind of link between these two approaches?
Right. Here, actually, what I took is, what I've done is just taking a linear combination of symmetries starting from M2, that's this non-local one, and some lower order ones. And then from there, try to see how I can derive an equation just for my function u. Right. So my equation and all the constraints lead to this system. So that is a little bit different because here the symmetry that I'm using involves sits only in one direction, does not involve any shift in the m direction.
And why is this a coupled system? Because it seems
no, this is already a decoupled one.
Yeah, that seems yeah.
Decoupled. Because let me just go to my board here. Hold on. Maybe, yes, because what I'm doing roughly, I'm just taking this equal to 0, and I have also this equation here.
Okay.
Right. So this system here actually can be decoupled, right? And so this is what I'm writing here.
Okay.
So that's why I'm saying this is different from what we've done, because what we've done with Vasilis was including shifts in both directions, right?
Yeah.
Yeah. Here I have just a symmetry which involves shifts in one direction, only shifts in n.
Okay, I understand. And this third order equation, we derived also, for instance, in the Caget's notes from when was it, 1996, we derived some third order equations associated with the KdV class. They were kind of like discrete versions of Painlevé 34. Is there any kind of
I think I've checked that equation, and I think they are not related.
Okay.
Yeah. But yeah, this is just one of the equations that I found, depending on how you, yeah. So yeah, I mean, it's a question mark what these equations are.
Yeah.
It looked like discrete Painlevé equations of third order, or as you've said, these probably Painlevé 34, but I don't know.
Yeah. Okay, interesting.
Okay. We can discuss about this.
Yeah, indeed. Okay, thanks a lot.
Can I ask something?
Yes.
In the example that you showed, the discrete potential KdV with a 5-dimensional algebra, one of the generators had dependence on n, right?
Hold on. Here, yeah. These are the point symmetries.
Yes.
Yeah.
Yeah. So M1, is it like a master symmetry?
No, this is master symmetry.
Which one? Yes, this M1. This is what I said.
M1 is, no, but this does not depend on M. Depends only on N. That you said N and M. Yeah. Okay. Yeah. This is the master symmetry. Yeah. Well, in this context, yes, this is a master symmetry.
So can you derive higher symmetries using?
Yeah. Just the commutator of M1 and G1 will give me G2 of, and so on and so forth. Yeah.
Okay. And something else, maybe. In the higher order lattice equation that you showed, I didn't understand kind of the rule that you presented.
Okay, yeah. Okay, this is something.
So is this like a
okay, here,
rule?
okay. what is the rule here? So what I want to do, I want to start from this point here, right, and end there by moving right up. Okay, so there are three different ways: either this way, right, and for this way, I represent, if you want, or associate with this way the product of the values of u at these four vertices. U at this point times u here plus times u here times u there. This is the first step. This is the product which is associated with this path, right? The second is associated with this path.
I see.
Right? And
then
finally,
one more with the
the other one is that one, yeah.
But then why is this kind of, does this, like, I didn't understand the statement. Does this imply?
Equal to a constant, right? This is an integrable equation. And you can solve that, and that you can find the symmetry of this equation. And actually, this is, yeah.
But did you derive the equation in this way, or?
Exactly.
Okay.
Yeah. And actually, you can derive not only this, but you can do this. And this is a paper that on consistent systems, which appeared for Journal Physics A. You can not only this, but you can also derive in the same way equations which involve 4 or more points. Right, so find all the paths from starting from here, ending there by moving either right or up, and with every path you associate a product, as I've said, and this sum of all these paths of all these products equal to a constant is another integrable equation.
I see. Okay. Thanks.
And yeah, thank you. More details you can find on that paper that I've said.
Can I also ask something? I understand how you can construct the symmetries for a given system. Can you go backwards? Like if you have a convenient map from something to something, can you construct a system for which this is a symmetry?
I mean, the same symmetry, the same function, if you want, could be the symmetry for many different systems.
Yeah, okay.
Yeah. It's very difficult to go back.
Then do you also have examples, like for instance for the ABS, of symmetries that are mapping solutions of one system to solutions of another system?
No, symmetries are by definition a transformation of solution of the system to the system, so to the same system.
So there is not such a concept of, okay, maybe don't call it symmetry, but something more, call it something different.
Do you have in your mind Becklund transformation?
Yeah, I do have Becklund transformation. Something. Well, the one difference between symmetries and Becklund is also a kind of a symmetry, but it maps a solution to a family. So it's not a map; it's a correspondence. So I was thinking of something like that. Yeah, some symmetry with respect to your definition. That
well, Becklund transformations do not form a group.
Yeah, but I mean, I said this is a difference. But do you have something that like looks like your symmetries that map solutions of an equation to another? Solutions on a...
Well, what we can do always is just, you can always take say a conservation law and use it to see if you can use it as a to do a potentiation. Right, for instance, between H1 and H2, or potential KdV and the equation H2 in the ABS classification, we have this. And the other is, of course, involves shifting the M direction in the second direction, right? Right. Actually, this follows from conservation law. So there's a potential for, and U here satisfies that what I've called here discrete potential KB or H1 in the ABS terminology, and V satisfies H2. And this comes from a conservation law.
Yeah.
Okay.
Yeah. And maybe one question, I don't know if it makes sense, but I'll give it a try. So, you know, like in the work of Pavlos, the other Pavlos and Matze, they are using first integrals in separable variables of maps to construct quad graph systems. And in your construction, there are several conservation laws which give rise to first integrals in separable variables. Well, there are first integrals for difference equations, but it doesn't really matter, because actually you can translate the symmetries of a map to the symmetry in the language of the first integrals of the difference system. So so this first integrals in separable variables give rise to potentials, and that's how they construct their systems, if I'm not mistaken. So do you understand that the symmetries of
it's a first conservation law? It's like, well, here in this case is this potential that I've shown you here, right? Again, this is what you do. You start with a conservation law of an equation. You use it to introduce a potential, right? And then it, of course, doesn't mean that it works for every conservation law, right? You can find a sort of better transformation between an equation between your original equation and an equation satisfied by the potential.
Okay, yeah. Okay, I got it. Yeah. Yeah. Okay. Yeah. Thanks.
And if we go to reductions, then usually you just use with a partial difference equation like this one, like H1 or whatever equation here, then you perform a periodic reduction. Usually the conservation laws will be reduced to first integrals for your map.
Okay, thanks. So are there any other questions or comments? Then okay, then we should probably end the seminar. So thanks again, Paulos, very much for your talk, and feel free to continue another time.
Okay, you are welcome.